The number 12,773 kilowatt hours represents the total kilowatt hours used since the last billing period. The number 0.788 kilowatts indicates the real power, measured in kilowatts, at the exact time the meter was read. The value 759,792 signifies the total cumulative kilowatt hours used since the electric meter was initially installed. Lastly, the number 20 represents the power factor as a percentage, in this case 20%. Let's delve deeper into each of these concepts to provide a more comprehensive understanding. Firstly, kilowatt hours, often abbreviated as kilowatt hours, is a unit of energy representing the amount of energy used by 1 kilowatt device operating for 1 hour. It's the standard unit of energy consumption used by electric utility companies to bill customers for their electricity usage. To calculate the energy consumption in kilowatt hours, you multiply the power in kilowatts by the time in hours. For example, if a 100-watt light bulb, which is 0.1 kilowatts, is left on for 10 hours, it consumes 1 kilowatt hour of energy, calculated as 0.1 kilowatts multiplied by 10 hours. Secondly, real power, also known as active power or true power, is the power that performs useful work in an electrical circuit. It's the actual power dissipated by the load, measured in kilowatts or watts. Real power is different from apparent power, which is the product of voltage and current without considering the phase angle between them. In alternating current, AC circuits, the voltage and current waveforms may not be perfectly aligned. The phase angle between them affects the amount of real power delivered to the load. Real power is calculated as voltage multiplied by current multiplied by the power factor. Thirdly, the power factor is a dimensionless number between 0 and 1 that represents the ratio of real power to apparent power in an AC circuit. It indicates how effectively electrical power is being used. A power factor of 1 means that all the power supplied to the circuit is being used to perform useful work, while a power factor less than 1 indicates that some of the power is being wasted due to reactive components like inductors and capacitors. A low power factor can lead to increased energy costs, overloaded circuits, and voltage drops. Utility companies often penalize customers with low power factors because it reduces the efficiency of the power grid. The power factor can be improved by adding power factor correction capacitors to the electrical system, which counteract the effects of inductive loads and bring the power factor closer to 1. Understanding power factor is crucial for optimizing energy usage and reducing electricity costs. Now let's discuss further how these readings relate to a 208-volt, 3-phase, 1000-amp electrical system. A 208-volt, 3-phase system is a common type of electrical service used in commercial and industrial buildings. It consists of 3 alternating current voltages that are 120 degrees out of phase with each other. This configuration provides a more efficient and balanced power distribution compared to single-phase systems. The 1000-amp rating refers to the maximum current carrying capacity of the electrical meter and the associated service equipment. It indicates the amount of electrical current that can safely flow through the system without overloading the components. The peak demand of an electrical system is the maximum amount of power that the system draws at any given time. It's an important factor in determining the size of the electrical service and the capacity of the equipment. Peak demand is typically measured in kilowatts or kilovolt amps. Estimating the peak demand of a 208-volt, 3-phase, 1000-amp system requires considering the types of loads connected to the system, their power requirements, and their duty cycles. The duty cycle is the percentage of time that a load is operating at its full power rating. For example, a motor that runs continuously has a 100% duty cycle, while a motor that only runs intermittently has a lower duty cycle. To calculate the approximate peak demand, you would need to add up the power requirements of all the loads that are likely to be operating simultaneously. This calculation should take into account the duty cycles of the loads and any diversity factors that may apply. A diversity factor is a ratio that accounts for the fact that not all loads will be operating at their full power rating at the same time. For example, If a building has multiple air conditioning units, it's unlikely that all of them will be running at their maximum capacity simultaneously. Therefore, a diversity factor can be applied to reduce the estimated peak demand. In a specific scenario of a 208-volt, 3-phase, 1000 amp electric meter, the theoretical maximum demand would be calculated as follows. The formula for calculating the apparent power in a 3-phase system is apparent power equals the square root of 3 multiplied by voltage multiplied by current. In this case, the voltage is 208 volts and the current is 1000 amps. Therefore, the apparent power is the square root of 3 multiplied by 208 volts multiplied by 1000 amps, which equals approximately 360 kilovolt amps. To convert the apparent power to real power, you need to multiply it by the power factor. If the power factor is 1, then the real power is equal to the apparent power, which is 360 kilowatts. However, if the power factor is less than 1, then the real power will be lower than 360 kilowatts. In this case, the electric meter reading indicates a power factor of 20%, which is 0.2. Therefore, the real power at the time of the reading is 0.2 multiplied by 360 kilovolt amps, which equals 72 kilowatts. This value is significantly lower than the theoretical maximum demand of 360 kilowatts, which suggests that the electrical system was not operating at its full capacity at the time the meter was read. To accurately determine the peak demand of the system, it would be necessary to monitor the power consumption over a period of time and record the maximum demand that occurred during that period. This can be done using a power meter or a data logger. Let's explore some additional considerations related to electric meter readings and power consumption. Electric meters are designed to accurately measure the amount of energy consumed by a building or facility. However, there are several factors that can affect the accuracy of the meter readings. One factor is the calibration of the meter. Electric meters should be periodically calibrated to ensure that they are measuring energy consumption accurately. Over time, the components of the meter can drift, which can lead to inaccurate readings. Another factor that can affect meter readings is voltage fluctuations. If the voltage supplied to the building is consistently higher or lower than the nominal voltage, it can affect the accuracy of the meter reading. Voltage fluctuations can be caused by a variety of factors, such as changes in the load on the power grid or problems with the local distribution system. Another consideration is the presence of harmonic currents. Harmonic currents are non-sinusoidal currents that can be generated by electronic devices such as computers, variable frequency drives, and LED lighting. Harmonic currents can distort the voltage waveform and lead to inaccurate meter readings. In some cases, harmonic currents can also cause damage to electrical equipment. To mitigate the effects of harmonic currents, it may be necessary to install harmonic filters. In addition to these factors, it's important to ensure that the electric meter is properly installed and maintained. The meter should be mounted securely and protected from the elements. The connections to the meter should be tight and free of corrosion. If the meter is damaged or malfunctioning, it should be replaced immediately. Now let's discuss some strategies for reducing energy consumption and lowering electricity costs. There are many ways to reduce energy consumption in a building or facility. Some common strategies include improving insulation, sealing air leaks, installing energy-efficient lighting, and upgrading to more efficient appliances and equipment. Improving insulation can help to reduce heat loss in the winter and heat gain in the summer, which can lower heating and cooling costs. Sealing air leaks can also help to reduce energy consumption by preventing drafts and reducing the amount of air that needs to be heated or cooled. Installing energy-efficient lighting, such as LED bulbs, can significantly reduce energy consumption compared to traditional incandescent bulbs. Upgrading to more efficient appliances and equipment, such as refrigerators, air conditioners, and water heaters, can also save energy and lower electricity costs. In addition to these strategies, it's important to educate occupants about energy conservation. Occupants can be encouraged to turn off lights when they leave a room, unplug electronic devices when they are not in use, and adjust thermostats to conserve energy. Another important aspect of energy management is monitoring energy consumption. By tracking energy usage over time, it's possible to identify areas where energy is being wasted and implement strategies to reduce consumption. Energy consumption can be monitored using a variety of tools such as energy management systems, smart meters, and data loggers. Finally, it's important to consider the impact of renewable energy sources. Renewable energy sources, such as solar panels and wind turbines, can generate electricity without producing greenhouse gas emissions. By installing renewable energy systems, it's possible to reduce reliance on fossil fuels and lower electricity costs. Renewable energy systems can also provide a hedge against rising energy prices. In summary, understanding electric meter readings is essential for managing energy consumption and controlling electricity costs. By understanding the meaning of the numbers on the meter, it's possible to track energy usage, identify areas where energy is being wasted, and implement strategies to reduce consumption. In the specific case of a 208-volt, 3-phase, 1000-amp electric meter, the readings provide valuable information about the power consumption of the electrical system. The kilowatt-hour readings indicate the total amount of energy consumed over a period of time, while the real power reading indicates the power being drawn at a specific point in time. The power factor reading indicates the efficiency of the electrical system. By monitoring these readings and implementing energy conservation strategies, it's possible to reduce energy consumption, lower electricity costs, and improve the sustainability of buildings and facilities. It is also important to note that a power factor of 20% is generally considered very low. A low power factor indicates that a significant portion of the electrical current is being used to create reactive power, which does not perform useful work. Reactive power is caused by inductive loads such as motors and transformers. A low power factor can lead to increased energy costs, overloaded circuits, and voltage drops. Utility companies often charge penalties for low power factors. To improve the power factor, it may be necessary to install power factor correction capacitors. Power factor correction capacitors are devices that store and release reactive power, which helps offset the effects of inductive loads. By improving the power factor, it's possible to reduce energy costs, improve the efficiency of the electrical system, and avoid penalties from the utility company. The size and number of capacitors needed will depend on the specific characteristics of the electrical system. A qualified electrical engineer can perform a power factor study to determine the appropriate size and number of capacitors needed. In addition to installing power factor correction capacitors, there are other steps that can be taken to improve the power factor. These steps include using energy-efficient motors and transformers, minimizing the use of inductive loads, and avoiding oversizing electrical equipment. Using energy-efficient motors and transformers can reduce the amount of reactive power consumed by these devices. Minimizing the use of inductive loads can also help to improve the power factor. Avoiding oversizing electrical equipment can prevent the equipment from operating at low power factors. Another consideration is the potential for demand charges. Demand charges are fees charged by utility companies based on the peak demand of the electrical system. Peak demand is the maximum amount of power that the system draws at any given time. Demand charges can be a significant portion of the electricity bill, especially for commercial and industrial customers. To reduce demand charges, it's important to manage the peak demand of the electrical system. This can be done by scheduling operations to avoid simultaneous use of multiple high-power loads, using energy storage systems to shave peak demand, and implementing demand response programs. Scheduling operations to avoid simultaneous use of multiple high-power loads can help to reduce the peak demand. Using energy storage systems to shave peak demand can also help to reduce demand charges. Demand response programs are programs offered by utility companies that provide incentives for customers to reduce their demand during peak periods. By participating in demand response programs, customers can earn credits or rebates that can offset their electricity costs.